Welcome everybody to Science Disrupted, the breakout session sponsored by DARPA's Defense Sciences Office, DSO. My name is Ivan Amato. I'm part of the communications team of DARPA, and I will be moderating what I'm sure will be an engaging, provocative, and hopefully for some of you, maybe even a catalytic discussion over the next 70 minutes or so. The Defense Sciences Office is one of DARPA's 6 technical offices, and those are the offices that conceive of and orchestrate the advanced research projects. That's the ARP of DARPA. And among the 6 offices, DSO is most immersed in fundamental science and mathematics as it strives to transform existing arenas of science and technology, and even at times to create new ones. Now, before I sort of get us into the discussion phase of this, I just want to share with you a kind of realization that I've been having during this amazing event. You know, as I'm listening to the main talks and I'm out in the demo hall, and I'm realizing that we're right here now in the present, and we're at a conference called Wait What? A Future Technology Forum. And so what that means is that we are now at a forum happening in the future. It does not get more DARPA than that. Thanks for laughing. So let me move a little bit more toward the program. And to begin that, I want to parse out the name of this breakout session, Science Disrupted, Beyond the Limits of Computation, Intuition, and Measurement. So the only thing I'm going to say about science is something that I think we can all agree about, which is that it is the most powerful framework for provisional knowledge generation that the world has ever seen. Disruption. Well, that's a kind of word that the pundit class took a hold of about 2 decades ago and started to apply it to anything in the human experience in which the rate of change is occurring at a rate faster than, say, evolutionary or incremental. Now, if we apply that idea of disruption to recent history, by which I mean, say, 500 years, the greatest disruption, perhaps, is the one that we often refer to as the scientific revolution. But when I think about that, I'm also thinking about how science begets technology, and how technology then begets tools that lets us do more science, and that how that entire dynamic ends up creating more than incremental change in just about every aspect of our lives. And so I would argue, and I bet you would agree with me, that science disrupted disruption. And so one of the themes here that I want you to think about is whether we are on a cusp where the disruptor of disruption is itself poised for disruption. Okay. And one other thing I also want to invite you to do, and this steals just a little bit of the thunder from the program managers who will be speaking to you in a moment, but it's a theme also that we've heard about already, which is this coevolution of machine and human intelligence towards some kind of hyperintelligence, some kind of super-organismal intelligence that perhaps is going to be necessary if we're going to continue to successfully take on and try to understand ever more complex natural phenomena, and if we are to continue to innovate and manage ever more complex technological systems. And so what I want you to do is in some ways join together in a behavior today that will, in a way, illustrate this human-machine hybridization. So what that means is I want you to sort of experience this and engage all of us in this room today with your heads up and your heads down. When your heads are up, it's kind of normal. You're paying attention to what's happening up here. You'll be paying attention to what your co-attendees might be asking or saying when they come up to the microphones that you see distributed here. And so that's going to be a sort of groupthink. But the only way that groupthink can really happen is by an interaction with a kind of machine intelligence, a machine brain. And by that, I'm really referring to all of the chips and all of the other technologies in the smartphones that you have, and the way those are attached to computers and communication systems and all of the other sets of technologies that go into making that work. And so by engaging heads down at times, and I emphasize at times, I want you to be paying attention most of the time up here with your heads up. But by doing that, in a way, we all will be participating in a kind of human-machine hybridization. Okay. So the way things are going to unfold now is that I will bring up in sequence our three program managers. I will start with Jim Gimlet, who will take on this idea of a hybridization of human and machine intelligence as we embrace ever more complex systems in both the natural and constructed landscapes. Following Jim will be Fariba Faroux, who will be taking us on a tour of some of the mathematical, algorithmic, statistical, and other frameworks that it is likely to take in order to really wrestle with the kinds of complexities that are going to be feeding into this kind of hybrid intelligence. And then finishing us off will be, in the best of ways, is Tyler McQuaid, who will take us down, in a sense, from these mathematical stratospheric heights that Fariba will take us up to. And by that, I mean he will take us into the periodic table of the chemical elements, so it doesn't get more earthy than that. And he will talk to us about how is it possible to go into a framework like that, which really represents a kind of infinite search space for the molecules and materials that will become the flesh of future technologies. And I hope that all of you will check out the speakers tab on your app if you want to find out more biographical information about our discussion leaders today. Now, after our discussion leaders finish with their talks, I will then initiate a discussion on stage with them, but then I will quickly open up that discussion to the floor. And all the while, I really do hope that you're taking note, you're paying attention to what's disturbing you, what's wrinkling your brow, so that when we get to that discussion phase, you'll be really motivated to come up and tell us what you're thinking and ask your questions and share your comments. And then if we still have time after that, I'll finish up by inviting all of you to share with us and your co-attendees what you think can or should be a next great disruption in some arena of science and technology that you care about. So let's begin. Let me ask Jim Gimlet to come on up.
Thanks, Ivan, and I'm really excited to be here and be part of this dialogue, and I hope it is a dialogue as we get going, and to help introduce these topics of science disrupted and complexity, and perhaps pose a few ideas of a disruption of disruptions. So as Ivan was saying, science is a recursive process. It both disrupts and in turn is disrupted by its own discoveries. And those may be new mathematics, new physics, new technologies, even new ways of doing science itself. And that's what I'd most like to talk about, this latter, as made possible by the former. But to start out, let's go back a few hundred years and talk about one of science's great disruptors, Isaac Newton. You'll see there's hopefully some method in my madness here. So humans are very good at finding and interpreting patterns. The Mayans found patterns in the sky and from that predicted lunar eclipses. But Newton disrupted science itself by essentially taking those same sky observations, combining it with what was known about gravity on Earth, and from that deducing his equations of motion and gravity that totally changed the way we do science. It went way beyond pattern matching. So what Newton gave us was a predictive mathematical model that closed the loop between observation and experiment and prediction and theory. This really changed everything. Of course, he had to invent calculus in the process. Disruption, as Ivan said, builds upon disruption. So the printing press, radio, television, these were all disruptive in their power to disseminate information. In terms of scale, however, the internet and this modern information age that we all live in dwarfs everything that came before. Information technology drives the loop of scientific recursion in sort of an exponentially accelerating process. And I'd maintain that we're really still only scratching the surface of the power that we already have at our fingertips. So also advancing exponentially is the complexity of the problems we're actually asking science to address, which may be modeling of complex molecules and materials, as my colleague Tyler is going to talk about, modeling of climate, of ecosystems, gene networks, the human brain. All of these complex systems are examples of high dimensionality, nonlinear, dynamic, multi-scale processes where our conventional tools really start to break down. We can only start to think about these hard problems because of where science has taken us, but it seems like even as we advance the power of our understanding, science is always one or two steps ahead. The challenges are one or two steps ahead of us. The nature of science has also changed. So we started out as kind of the basement scientist, the singular genius like the Newton or the Einstein, who somehow came up with incredible intuitive leaps and totally changed our understanding of the way the world works. Today, science is a much more collective enterprise. That low-hanging fruit's been mostly picked. And we more increasingly rely upon machine help to crunch vast quantities of data that a single human brain has trouble taking in. We're still pretty good at tackling problems that can easily be decomposed, so putting a man on the moon or a probe on Mars. Unfortunately, many of the complex problems like those that I mentioned earlier seem to be beyond what a single brain can easily process. We need new mathematics and physics to help us out, but perhaps we also need a new way of approaching the science. So this is the challenge that I'd like to pose to this audience here, this community. How do we scale human and machine intelligence to tackle these kinds of problems that are difficult to decompose? How do we scale, how do we create an ensemble of scientists and machines that are more than the sum of their parts? Accomplishing this perhaps would pose the ultimate scientific disruption and might even give some credibility to this idea of information explosion or technological singularity. But first, on the scaling of intelligence, I say intelligence because that's really what we're asking. We're asking for new methods to convert data, vast quantities of data, into knowledge, into understanding, ultimately into wisdom. We've come a long way with machine learning techniques to find high-level abstractions in data and correlations in data. And our deep learning techniques, based on multi-layered neural network structures, can now tackle all kinds of interesting application domains, from games, as we heard earlier this morning, voice recognition, image recognition, even language processing. So these are all accomplishments this community can be proud of. Unfortunately, the machine still remains the weak link in our idea of scaled human-machine interaction. In fact, I would maintain that in a few decades from now, I'll probably incur the wrath of many of you, we're going to look back at our deep learning techniques pretty much as the pattern matching and numerology of, for example, the ancient Mayans. So going back to Newton, suppose we did feed a bunch of high-resolution photos into a deep learning pipeline. Could it predict the future position of planets and stars? Probably yes. Could it deduce Newton's laws of motion? I don't think so. I think it's not architected for that. It doesn't have a good representation of time, for example. It can't draw upon prior knowledge. It has no adaptive model of the world. It has no abilities to synthesize and imagine alternate future paths. And also note that a child doesn't need a million training sets to recognize a cat, and Newton did not need that much data to figure out gravity. So we're doing something that's not quite right. How are we going to possibly solve these more complex problems? I think we need another Newtonian revolution with better architectures, algorithms, learning techniques in our machine learning methods to constrain top-down data-driven discovery techniques with bottoms-up physics. And like Newton, we're probably going to have to come up with better mathematics, as my colleague Fariba is going to talk about. To close, let's not ignore the possibility that the human no longer remains the only creative driving force in this loop. So nobody knows really the capacity of the human brain and how close or far away we are with our engineered silicon to achieve or even surpass the things that our evolved carbon can do. So we heard this morning, and I'm sure all of you have heard the cautionary words of folks like Bill Gates, Elon Musk, Stephen Hawking, about the dangers of artificial intelligence. So I can't avoid that subject. We're just not comfortable with the idea that there could be an intelligence on the planet that's equal or possibly surpasses our own, perhaps for good reason. I'd also argue, however, that ever more intelligent machines are our intellectual offspring, and they're a logical outcome of recursive science. I haven't really seen too many deeply reasoned analyses in this debate. I think it's too early, at least for me, to take sides even. I'd only observe that machine intelligence is moving forward. It's being pushed by all manner of stakeholders in the community, in all manner of applications, defense-related, commercially related, and in all corners of the globe. So there's no looking back. And we need more intelligence in our machines in order to meet the human at least halfway in this grand vision of scaled human-machine intelligence and collaboration. I'd also maintain that it's DARPA's responsibility to push forward to explore both the technologies and their consequences to understand better where we are in this process of scaling intelligence in this human-machine collaboration, of course, in the most enlightened and responsible way possible, and with the help of communities like yours. I think that the notion of technological singularity is a theoretical construct which may or may not be an evolutionary inevitability. Even if it is, it's our responsibility as individuals and collectively to shape our own future, to push through, break on through to the other side if we have to, and not derail. So we have to use our own imagination, creativity, and intelligence to create intelligent, creative machines that are going to be trustworthy, collaborative partners in this scaled intelligence endeavor. And I'd like to invite all of you to be collaborators in that process. Thanks.
Well, thank you, Jim. I think the only thing I'm going to take exception with there was your statement that we're not very comfortable with other kinds of intelligence surpassing our own. I'm speaking only for myself here, but it's actually a familiar experience for me that other intelligences are surpassing mine. So when machine intelligence does that, I think I'm going to be okay with it. So let me now segue to our second speaker, Fariba Farouk. So if innovation in any branch of human knowledge has a chance of taming the tsunamis of data and complexity that Jim spoke about, it will be probably in the arenas of in the arena of mathematics and some of the other frameworks that Fariba will talk about. So therein lies the pathway from an era that is data-rich and insight-poor to one of deeper understanding about the complex phenomena that we are engaging and caring more and more about. So Fariba, please.
Thank you, Ivan, for your introduction. And thank you, Jim, for setting the stage for our discussion on current limitation in modeling our complex systems. Jim is asking for radically new approaches for modeling complex systems based on human-machine intelligence. His talk brings out a theme in my own thoughts that in the 21st century, we are both enabled and encumbered by the major advances in two areas: data and computation. Been hearing quite a bit about this. With computational power, now there is this promise of better modeling techniques. And with data, there is this promise that maybe we get more information about our complex systems. But these promises have not been realized. computational power, more computational power has not given us better predictive models. And more data has not necessarily led to better and deeper insight about the system we like to study. And I believe it's all because of the challenges that are due to complex nature of these systems, and they are in the issues such as the scales, the curse of dimensionality, the high dimensionality of the systems, and the massive uncertainty that we have about our systems and models. If we don't address these challenges, then we cannot really have, we cannot really harness the power of data and computation. And now there is this call to arms from mathematics to take center stage. This is great, because now we like mathematics to provide us with new frameworks, new abstractions, and new tools for discovery. I ask myself, why math? But if you look at the history of mathematics, in fact, it has always been at the center of scientific discovery. It's been called the queen of sciences. It's been actually considered, and it's been embraced by all nations and cultures across the globe as the universal language of science. But mathematics at this point has two phases. One phase is turned towards more abstraction, which we call pure math, and one turns externally towards the application and the physical world. It's a duality, but now this duality has turned into stark divisions. I don't want to dwell on this kind of duality and the kind of division, because I think that's the stumbling block for mathematics to realize its power. Whether mathematical research is externally or internally motivated, its goal has always been to discover and understand deep connections and patterns, as Jim has said. And when these connections across different fields are made, that's when mathematics has been a disruptive element in scientific discovery. There's been lots of examples. One that Jim has been talking about, and that's really starting with Newton. And that's the deep synergy between Newtonian mechanics and calculus, between the abstract notion of Riemannian geometry and Einstein's theory of general relativity, or Hilbert's operator theory and modern quantum mechanics, vector fiber bundles, and the theoretical particle physics. There's been lots of success stories about the deep connection between mathematical work and physics. We can call that basically the external world. But what is really the failure? Are we really succeeding? Because these are all success stories. And in my belief, it's my opinion that not yet. What we are failing right now is that we are failing to make the necessary connections across this different field and really meet the challenges that, as I've been mentioning, I really want to emphasize that have to do with the high dimensionality of the systems, nonlinear dynamics of the system, as well as the stochasticity of these systems. There have been lots of beautiful theories, in fact, lots of powerful theories that address these challenges, but separately. What we need is to address these challenges within the same framework. Let's talk a little bit more about these challenges. Dynamics. Information technologies, almost every system of interest, information technologies, sensor networks, communication systems, genomics, climate, ecosystems, these are all examples of dynamical systems. And the data that we get from this system, if we want to analyze this data, that means this data correspond to, again, dynamical systems, meaning that they change and the behavior changes with respect to time. Now, in this technical forum, we have heard that data has shape, but it also has dynamics, meaning the shape and behavior is going to change with respect to time. I've been emphasizing that. But with all the advancement that so far we've had in our statistical analysis, data analytics, machine learning, this aspect has not been incorporated in the kind of problems that we are interested in. We had a beautiful theory of dynamical systems, right? But this theory has not been incorporated. So that's one major challenge, and that's how I think it could be addressed. The other challenge, high dimensionality. Both our data system, computational system, they are saddled with the case of a curse of dimensionality. What it means is that the cost of computation is going to increase exponentially with respect to the number of variables. I have no idea how many papers I have looked at, research areas I've looked at, where people are saying that we can overcome the curse of dimensionality. Okay. I'm not quite sure whether we are quite there yet. But in the meantime, what we can do about mitigating this issue of dealing with high dimensionality is coming up with very sophisticated techniques for better compressed representation of our data and models. This is where I think we should go beyond numerical linear algebra. What we need to do actually is use ideas from geometry, from information theory, in order to come up with a more compressed representation. And the last one, randomness, stochasticity in our data and computational models. The data we have are highly noisy, incomplete, and often also the parameters that we have in our computational models, either they are unknown or they correspond to random fluctuation in our systems. So how do we characterize this? How do we incorporate this randomness and also this uncertainty that we have into our analysis and into our modeling and later on about our design? This is a major challenge. Now, in conclusion, I'm highly confident that mathematics has the power to confront this, confront the challenges that I mentioned. But in order to do so, what we need is a combination of bringing together the rigor of mathematical thinking and research into our more heuristic approaches to modeling. If we don't do that, what we're going to have, especially nowadays, we have more computational power, we have more data. What we're going to do is that we're going to come up with these algorithms that converge to something, but we have no idea why they converge and what they converge to. If we want better understanding and deeper understanding of these methodologies, and as well as having some confidence about these methodologies, we really need to put our mathematical research right in the center. The way we ask questions, the way we pose questions and answer questions about data and computation. I think that this is how we can make the leap, or actually the connections that I really think needs to be done across these different fields in order to make mathematics really the disruptive element in our scientific discovery. Thank you.
Thank you, Fariba. And actually, before I do bring Tyler up, there were just a couple of things about the app that I should have said earlier. So one of them is that the best way to interact here is by accessing the activity feed for this particular session. And the way you do that is by going to the schedule at the top of your app, scrolling down to this very session, which is Science Disrupted 1, then hitting the activity button at the top. And then what that does is actually then puts whatever comments or questions you're in into a specific sort of feed that all of you who are doing that same thing would see. And in addition, DSO has put up a survey question that we invite all of you to look at and respond to at your leisure, at your will, but it will be another way of kind of interacting in a little bit of an ongoing way. And we promise to look at those. The question is the one about what do you think might be a really great next disruption in some area of science and technology, with a second question of why. And then we'll take a look at those and compile those in some way and hopefully present those on the DARPA website in the future, and we'll let you know about that. So let us move then to our third discussion leader. So as logic, methods, and tools of scientific investigation morph, so too will the character of one of the most important bases of scientific discovery and technological innovation, materials science and engineering. And I invite Tyler to come up and give you his view of this amazing place, the periodic table, of the chemical elements and how he plans to discover the future of technology, at least the flesh of it, in the form of molecules and new materials. Tyler.
Ivan, thank you. I would like to start by taking a moment. For those of you who hadn't had an opportunity to look at Ivan's bio sketch, I just want to let you know he's a talented science journalist and has been doing this for quite some time. And there were hours spent before we crafted what you see today, spent with Ivan helping us, coaching us, trying to get us to narrow our messages down to a bite-sized morsel. I mean, Jim, physics in 20 minutes, Friba, math in 20 minutes. You know, I'm going to try to do chemistry in 7, mainly because they've decided chemistry is just less important. But if you could just take a moment with me and thank Ivan for helping make this possible. So I'm very happy to be here. DARPA is a wonderful environment to work in. My colleagues are exceptional. The opportunity to transform science is a once-in-a-lifetime opportunity. Now, I'm a molecular scientist, and throughout this meeting, I see molecules in everything. I see molecules in CubeSats. I see molecules in three-dimensional chips. I see molecules in almost all of our talks. Trillions of sensors, who's going to make that happen? Yes, engineers, but those base materials that are going to be used to make those sensors for a cent each so they can be distributed out in the world, that's going to come down to chemists or molecules. So I love chemistry. Yes, I said that. Now, how many of you love chemistry? Now, we're going to participate, so come on. Wow, okay. How many of you don't give a damn about chemistry? Now, you got to be honest with me. Thank you back there. And how many of you dislike chemistry, find it to be the dirty science? Okay, so I see that I have some challenge. I want to take those ambivalent people and move them into the like chemistry, and I'll settle for ambivalence from those people who said they didn't like it. So that's what we're going to try to achieve in the next 5 minutes. So I've been examining molecules and materials for my entire adult life, and it's been fun. And I really think that chemistry offers this great opportunity to really explore the limits of intuition, the limits of measurement, and the limits of computation. So like Jim, I have a universe here to show some vastness. So when we consider the periodic table, we have 100 atoms that we can mix and match. We can play with bonding, we can craft molecules, we can craft macromolecules. Now there are estimated 10 to the 28 stars. That's a lot of stars. But based on our understanding of bonding principles and the periodic table, there are estimated to be 10 to the 60 possible molecules that we could craft. And it's really, that's a way underestimation when you start to take into account things like sequence-controlled polymers that some could have billions and billions, 10 to the 60, 10 to the 70 type possible iterations. So that's an infinite design space. I think really some of the limitations and challenges are this infinite design space. What do we make next? I mean, in this presentation of talks that have happened over the last couple days, we've seen lots of cool new things, many of them built off of materials that have been around for 50 years. My wonder is, where can we go if we had a new set of tools? And how do we get there? And what are those limitations? So in my mind, how can we disrupt molecular sciences so we can better help all of you do your jobs, those engineers in the audience, those technologists, how can we help you do your jobs better, is to create new tools to help us survey this galaxy of possibilities. And those tools are going to come in intuition. And to me, intuition is related to making. A lot of people who make molecules use a heuristic approach, very much an intuition-based approach, because we're talking about a lot of complexity to build a molecule, a lot of possibility spaces, and we haven't gotten really good at dealing with that complexity. In addition, measurement, that's characterization in my world. We need to understand the material we've made. What is the composition from an atom standpoint? What is its property composition? So we can let you engineers know what this molecule might be good for so you can plug it in to your design iteration. And then finally, computation to me is theory. You don't do chemical computation any longer, or chemical theory without computation. Okay, so let's talk about making. Okay, in my mind, this design space, I'm surprised. You know, it's so big, 10 to the 60, that we've been able to do anything, that we've been able to find any good molecules, but we've done pretty good. We've borrowed ideas from nature. We've come up with our own algorithms. The pharmaceutical industry has spent trillions of dollars to help them with their designing of small molecules. So small molecules, we have drugs, we have liquid crystals to help us display these images. Macromolecules, we have photoresist, so all those CMOS junkies out there, you wouldn't live without our photoresist that my community helped bring to bear. Extended structures, so diamond coatings that we need to put on rotor blades so we don't have sand ablation, like Lee Rudisil talked about. I thought I saw him in this room. And then finally, ceramics and metals. I mean, if you look at material scientists and chemists, we're actually doing pretty good. I mean, we do offer you guys a large palette of things to put into the things you're gonna make, devices. But we still have a long way to go. Even though we're constantly making disruptions, I was gonna hold up my cell phone to talk about Gorilla Glass. I mean, glass is old, and we are still disrupting glass, right? I love my Gorilla Glass, it's really lovely. Anyway, you're supposed to chuckle just a little bit on that, yeah. We're gonna have to loosen you up a little because you're gonna have to come to the microphones. This is gonna be really boring. A panel is not what we want here. We want this like interactive soup of you guys coming up and challenging everything that we've said. But we have a long way to go, and how do I know we have a long way to go? Well, it's shown here. Nature makes us look silly. I mean, this is molecular organization across many length scales, from atoms all the way to in meters in some case. I mean, my leg muscle is pretty big, maybe not meters, I wish it was. Where's Adam Russell? He has a meter thigh muscle. And we're control over interfaces. Now think about this. These are control across length scales to create a variable tunable output material that self-repairs and reconfigures. I mean, I work out, it's not obvious, mine don't reconfigure as well as some others, but muscles tend to reconfigure pretty well. Okay, so the greatest limitation right now in terms of making things is we don't even have a context for this type of design. We do not have a CAD-like molecular algorithm for designing a system that takes into account all of the interfaces, all the molecules, all of the ways that you would build such a wonderful structure. So how would you change the molecules that we make or how they are made? I know a lot of you have probably gotten your hands on some nanotubes and then got your hands on a second batch of nanotubes and they don't work as well as the first batch. You know, how can we change the way you're receiving new materials? All right, so characterization. The nano investment that we have made has done wonders for our capacity to characterize nanoscopic materials. Now, this image that I show here could be maybe an SEM or a TEM of some ferrite magnetic particles or something like that. And we've gotten really good at making these measurements. We've gotten good at doing AFM measurements on nanotubes, for example. But one problem that we have is spanning the length scale. So for example, when you start to look at this one in sort of its full glory, well, no, it's Rodin's thinker, right? An image of it, a pointillist image. And this is a major problem in characterization. While we can do pretty well characterizing things on an atomistic level in terms of its composition or in a materials level in case of a nanometer type analysis, we really are bad at trying to understand how are those nanoscopic properties going to translate into materials. And we have people like John Main running A2P who is going to try to be able to build from nano up and retain some of those properties that were observed at the nanoscale. So to me, characterization has a lot of problems. Number one, I can build materials faster than I can characterize them. Now you might say, well, that doesn't make sense. Well, yes, it does, because typically it takes time to characterize the properties and the composition. Composition sometimes takes me weeks. Now, the other problem is this length scale issue and how to know whether or not the measurements you made on small scale will actually scale up. So we need to come up with better ways. And I see a number of different ways that we could do that. I see ways of taking a range of low-quality measurements and integrating them together in a multivariate analysis. So you could speed up how we are able to characterize. I also see leveraging quantum correlation approaches across different electromagnetic spectrum so that we could make the same type of NMR experiments in other wavelengths. So there are ways to go, but I'd like to hear what you think. How can we leverage things that you're doing to make discovery of materials faster, better, cheaper? Now finally, the last opportunity is the biggest opportunity, and this is in theory, and it relates to all of the other things that I've said. Now when you think of theory in chemistry, for those of you who actually took chemistry at some time that you actually remember it, which how many chemists do I have in the audience? Oh, right on. Okay, great. I got a few. But for those of you who aren't chemists, maybe you got some reaction theory, some kinetics, some thermodynamics. I know engineers, beat that upside down and backwards if you're chemical engineers. And you probably got some quantum mechanics, right? The dream of quantum mechanics was that we were going to be able to use these ab initio calculations to to model the properties of molecules from the electronic structure all the way up. But extended quantum mechanics is still really tough, and you oftentimes have to use a hybrid approach to achieve those objectives. And then we still even have a gap to continuum modeling. But that doesn't even start to scratch the surface of the muscle issue, right? I don't have a design palette to be able to contemplate even building that structure. So beyond the issues that we have in dealing with sort of ab initio computation, we need to come up with new ways of thinking about how we build materials from the ground up. Now, obviously, there's lots of advantages from not doing that. Stripping down materials is also certainly a way to go. But if we want to create ever more complex materials like the muscle, we need to have design tools that can achieve that objective. So I'd love to hear how you might help me with that effort in terms of giving me some of your insight. Okay, now while cyber communications and robotic disruptions are DARPA darlings, right? They're awesome. It's fun to go see the robots that you read about. Classic, not so hip molecular scientists are called to create the basic building blocks that you're going to need to build that ever more interesting robot. Right? If you look at robots, the servos and all the gear that we make them out of is really limiting. I think that chemists are going to have to, or molecular scientists, material scientists are going to have to come up with some new way for creating the building blocks if we're ever going to begin to realize the potential of automation, for example. So, help me figure out how we can better survey the galaxy of possibilities in molecular sciences. Thank you very much for your attention.
Thank you, Tyler. So we've covered a lot of ground here, it seems to me. We've gone from kind of electrons and atoms all the way up to a kind of human-machine superintelligence. So I'm really hoping that all of the subject matter that we've covered here has really perturbed you, disturbed you enough to want to get up to these microphones in just a moment. I'm going to get us into this sort of discussion mode by asking a question of our three discussion leaders. And I will invite you also to respond to that in your own ways if you're so moved. So what I'd like to ask of you, and in some ways this is directed a little bit more toward Jim, but I do invite Fariba and Tyler to weigh in as you might be so inclined. So, at the meeting we've been hearing a lot about this movement toward this coevolution of human and machine intelligence. And there's something that disturbs me about it, because as I think about that, I understand that we are interested in very complex phenomena. We're interested in understanding and managing incredibly complicated technological systems like the coming Internet of Things. But I keep hearing also that the only way we're going to understand and manage these things is through this kind of hybrid intelligence. But I really want to understand all this stuff in my own intelligence. And so it almost feels to me as though what we're doing is we're saying we're reaching perhaps the end of human intelligence in a sense. That we're not going to really be able to understand things in a satisfying way that perhaps we've understood things in the past. Now, I don't know if I'm too pessimistic, but I thought I'd throw that question at you, Jim, and to the other two discussion leaders as well. But Jim, what do you think?
I could give you a long answer or a short answer to that, and since we want to get you guys involved too, I'll give you the short answer, which, at least from my perspective, we're not seeing the end of human intelligence. We're seeing the beginning of extending human intelligence, and particularly, I want a way to overcome the biggest bottleneck that I have in thinking about complex problems is that I have very limited I/O bandwidth. I've got like 100 bits per second coming that I can absorb and probably retain about 2% of that. So I need the machine to help me distill knowledge in a way far beyond what we can do with Google search and popularity contest keyword searches. So I would say we're at the beginning of that process. and there's a lot more I could say about it, but we probably should move on, and then we can talk about this again and the idea of information explosion and the different sides of that debate.
That was a short answer.
Tully, do you want to elongate the answer?
Humans create tools, tools hurt people, you got to figure out how to make the tools safer. There's my answer.
All right, so I want to actually invite the audience to even respond to that question first before we might move on to other ones. Does anybody want to add to that little bit of our discussion now? Okay, if not, I think what I'll do is I'll go sequentially through from your left to my right at these three microphones. So the questioner on the left microphone or to the right of us on stage. Yes, sir.
So I have a comment for Jim's position here. You know, we've heard a lot about the trillion sensor world in this meeting, and I think the Moore's Law junkies and the comms guys, they love that because they need more I/O bandwidth, they need more cat videos, and that's going to keep driving the Moore's Law and the semiconductor guys forever. But I would argue that our problem is finite in this room, which is human knowledge. Human knowledge isn't growing nearly as fast as IT bandwidth. And I think as far as this problem is concerned, the IT hardware is done. You know, when I can carry, you know, we have to separate the useful human knowledge from the cat videos. But when I can carry all of the useful human knowledge on my cell phone, then we're done. And so then maybe we need to talk about algorithms, maybe we need to talk about how we're going to analyze this, but I think the body of human knowledge, of interesting human knowledge, is finite. And I would argue that our IT capabilities are already beyond that.
Robert, does that hold true if you have now a cell phone that can help you utilize that knowledge more effectively? So right now you're looking at it as a vassal for information to make sure you stay relevant, or I stay relevant. But you know, if you now have all the algorithms that Fariba is going to provide us, does that change your hardware?
Well, I'd say we have enough bandwidth. We have enough capacity. If I can put all of human knowledge, all of useful human knowledge, we'll call that the...
Memes are useful. Thank you.
If I can put all of the useful human knowledge into RAM, and I can transmit it all in a second, then our hardware is ready. I would agree that what we need is a new way of looking at it. We need the algorithms, we need the math, but I don't think we need a trillion sensors and terabytes per second of additional information to learn anymore. Like Jim points out, a million photos of the universe aren't going to give us Newton's laws. We need a new way of thinking about it, but we don't need better IT resources to do it.
I would disagree with that politely. I agree with what you're saying that human knowledge is, actually I disagree even with that. I think that is increasing exponentially. But what we're missing is, both on the complexity side of the problems, those are very under-constrained in data. So we do need more sensors, we do need more data, and we need better processing power to interpret that data in a way that our brains can then take in and figure out what's really going on in a meaningful way, in a predictive way. So I would argue that we need all of the above. I agree that possibly the way you've prioritized it is a good way to think about it, but we need the whole kit and caboodle.
So I would say this is about a 10-beer discussion a little bit later, but I want to make sure that we have opportunities for more of us to get involved in the discussion. Also, I should say, we do find ourselves quite interesting to one another. So if you're so inclined, please tell us a little bit about you, maybe who you are, for example. And that's not an obligation, but if you're so inclined, please do so. So I want to go to the gentleman in the middle.
I'm Mark Millis. I used to work for NASA. Two things came up when you were talking. First, on mathematics, there's still a lot there, because when you think about it, how much of our physics is based on equations that still have singularities, and how much is based on approximations on a simple harmonic oscillator? I mean, to go back to those and refine those could be a bit of a change. And then the second thing is that, like, even it came up again about the looking at simplicity, Newtonian type simplicity or complexity. our human cognitive biases really creep into how we do things, and I hope that AI will not have those. And the reason why I bring that up is because whether we realize it or not, we're starting to try and all agree on something because we're a group of people and we like to get along. Whereas that disparity between looking at something simply or looking at it from that complexity adds to covering the problem basis. And so hopefully with AI in the loop, without ego biases, without confirmation biases, without needing to jump on bandwagons, we'll be able to more quickly sift through a number of different possibilities and find solutions quicker. At least that's my hope. And I don't know if any of those thoughts might trigger any more reaction.
I'll take it over if you don't want to address the math question. I think part of the hope with AI is that humans do have one advantage. We're able to hierarchically construct a vision or coherent picture in our mind. So going back to Ivan's question, I don't have to know the details of every domain of physics or math that may apply to the problem I'm trying to solve. But as long as I can create at least some kind of hierarchical picture in my head that's coherent. So we're very good at doing that with building 737.
I can see that as a possibility, but not to the exclusion of the other.
Yeah, so I'm looking for AI to help translate things that I can't comprehend or that my brain plasticity will not process fast enough in my lifetime, so so I can still maintain a coherent hierarchical picture of the thing, but perhaps have a very distilled picture of, for example, topological math that may be applying to how to reduce the dimensionality of this complex problem that I want to solve, and I only can apply my statistical physics tools.
Oh, I can definitely see the value in the realm that you're talking about. I was also trying to draw attention that there's even utility on the other end of that, that there's more than one way looking at it.
So I'm missing maybe understanding.
You're talking about the value of AI to process all sorts of data and distill that down into some basic understandings that's beyond your comprehension to pick up readily.
That's part of it, yeah.
Okay. What I'm saying, yeah, I completely agree with that. There's the other side of when you get back to, say, Newtonian simplicity of basic physics, of going back to some of that stuff as well, but the value there is that those looking at different perspectives are without the cognitive biases of humans, of not, say for example, not wanting to try out a controversial idea because that might hurt your reputation. I don't see that coming up in AI.
Yeah,
and that those can also be part of the picture. Okay.
So I think this again is one of those very long discussions. I want to make sure that we can move on. We haven't even heard yet from a questioner on your right. So please, let's move over there for the first question from that microphone. I'm anxious to hear it.
Hi, thank you. My name is Raymond Weidekamp, and I'm an entrepreneur and a materials chemist. And so I have a pitch for you that maybe could perhaps solve Tyler's problems while touching on everything that we heard. And so that is, if we're going to be able to use machine learning and we're going to be able to use humans, scientific experts to, as you said, compress the data, right? You can't just have raw data out there. I think particularly in the materials case is an area where we need to incentivize and come up with structures for people to actually share the data itself as opposed to sharing their interpretation of the data as the publication. And so I really see this as something that, the reason I'm saying it's a pitch is, this is a DARPA implementable, funding resource, which is there's currently no incentive for me as a materials chemist who has the secret sauce recipe and who can get, my science paper and show off one aspect of the thing to reveal any of the other properties about my material, the spectra of the molecules. And, certain journals that are very specific have specific criteria, but they'll say, okay, you have to have a proton, a carbon, and a mass spec. That's actually the extreme. In materials chemistry, there's nothing like that. And honestly, my biggest frustration with applied physics and materials as a graduate student was complete irreproducibility of this stuff. So I feel like DARPA actually could truly incentivize researchers to share their data, and it doesn't have to be in a raw format that is inaccessible to these algorithms, but use the fact that we're smart enough to choose the useful features like the modulus, the spectra, all these things, use the humans as the compression, and then enable these algorithms on data sets that are not infinitely complex, but still include a whole lot more than the supporting information.
So this is a discussion that we've been having quite a bit in DSO. So Bill Regley, who I want to make sure I say something, his voice is gone. So I'm going to try to say things that make him want to talk, but he can't right now, which is awesome. So Bill wants to create a vassal where we put raw data into the vassal, and agnostically. Don't worry about interpretation. Just put the data in. And then the onus becomes on the person who wants to spelunk into that vassal to create algorithms that can recognize what the information is and then interpret it without interpretational bias that you might have already brought to the table. Now, I'm not saying that completely solves your problem. I know that the materials genome effort has tried to address some of the concerns you have, but we don't have an effort right now. We're talking about it, and I think you're absolutely right. And I think this crosses many different disciplines. The idea that we can put the information into a place where then you have the onus of creating a crawler, if you will, to pull that information out. Because I think if we put it in with too much interpretation, you run the risk of adding that bias that then we won't be able to get the full opportunity out of that information.
Yeah, absolutely. But I think the role that an organization like DARPA could do is to set the work with people in the field to set the standards for this is how this data is going to be put into this database. This is what you are and aren't allowed to do to it, and to incentivize people the way that everybody on the Human Genome Project agreed at the Bermuda meeting that they're all going to publish everything that they work on that. That's not true for other species, so people hold on to their secret genome sequences for other species, but not for humans. And I think materials and chemists in some ways are really the last of the Mohicans in holding out in this very, secret sauce kind of mentality. And I feel like an organization like yours could actually move the needle in terms of incentivizing people to share more.
I agree on all the points. The bottom line is we need that information in place so that we can then leverage some of the big data tools that biologists have created to mine their own data sets. So
One brief comment, sorry.
I'll allow that. Go ahead.
On the scaled human-machine intelligence. So it is a progression, and the first part of that progression, it may be just mining the already available literature, because I don't have the bandwidth to read the 10,000 papers that may apply to my complex climate modeling, for example. But the next part of that sequence is I want the machine to be able to go out and not just mine the distilled, published interpretation of the data. I want the machine to be able to access the raw data, the metadata, and the models that publisher, that performer put out as part of the process. So we have to totally change the publishing paradigm to get to this next step. So I totally agree with your premise.
Okay, so we've had 3 questions, and each one of them could have catalyzed an hours-long discussion. This is terrific. So I want to now move over to the mic on the left.
Hi, my name is John Randall. I represent Zyvex Labs. We were fortunate enough to win one of John Main's A2P programs that we're just getting started on. Let me say that I'm an engineer. I'm not a scientist. I love chemistry. Well, I love what it can do for me. I don't understand it very well. But the discussion here is especially about AI, and to some extent about advances in applied mathematics, center around not so much digital electronics as digital information theory. The world of information has been taken over by digital approaches because there's huge advantages in doing that. Noise immunity, ability to create enormously complex systems that perform with ridiculous reliability. I believe there's an analog possibility in the material world. The universe is made up of quantized matter. And we're trying to make a manufacturing process, first just a laboratory fabrication process, that can do what Feynman suggested back in 1959, put atoms where we want them. If we can make invariant structures in terms of the number and type of atoms that we want in the chemical bonding configuration that we want, then we can make physical systems that have some tolerance, and the tolerance being roughly what a chemical bond will put up with, to make way more complex, way more reliable systems than is currently possible. And we can extend these digital advantages. I think there's a lot of analogies. We can extend digital advantages into the material world. And I think that that's an idea that's worth pursuing. Certainly Xivex Labs is trying to do that.
Tyler, anything to say?
I mean, I just think we're at the infancy of the printing concept in material space, and I can't agree with you more. I think it's exciting. I'm really glad to see that one of my peers who I really enjoy talking to is working with you on that enterprise. I think you're going in the right direction, in my opinion.
All right, let's go to the central. Mike?
So my question is motivated by Tyler, and I'm interested in any of your responses. Chemists have done an incredibly good job of using their intuition. You take kids in freshman chemistry can go to the chemical stockroom. I can't take credit for this. This is one of my colleagues. And learn how to do chemistry with very little training. The question is simple. Can we ever teach machines the chemist algorithm?
I hope so. This isn't really about programmatic discussions, but we have an effort right now called Make It, which is designed around connecting a fundamental synthesizer, so something that can do what a freshman chemist can do, and attach that to AI. And Fariba is helping me evaluate those efforts, and we're hoping that together those two can both build off of some rules, some machine learning, some try to give it some heuristic capability, some planning capability as well. So the answer is I definitely think yes. I think it's going to be a progression. And I think it's a really important component, and it's one of the things that machines can do for us is to systematize any activity. And chemistry has largely not been systematized. Anybody in the audience who has tried to reproduce a chemical reaction will recognize that it's much more like a chef's recipe, very terse, very poorly crafted for reproduction. So it really slows down the process, makes reproducibility a major issue. So to answer your question in a nutshell, I absolutely think so. I think we're right on the precipice. There's lots of things that are coalescing together to begin to make that a reality.
Fantastic, thanks.
Thanks for the question. Let's move to the mic to your right.
Yes, hi, I'm Vlad Lieberman from MIT Lincoln Lab, and my interest in metamaterials and plasmonics mostly. And so my question is going back to the concept of disruption here. So the way I see this, especially kind of looking back to the Tom Diedrich's talk, is that we're going to have machine learning that's helping us, but the disruptions will come from the human element just because of the capability of the brain to recognize complex patterns and switch around. And so the question I have is it possible to design machine learning for disruption? I would introduce some kind of stochastic element there, some kind of interruption, some kind of randomness into the machine learning process itself, so it can come up with some unusual concepts that it wouldn't necessarily evolutionarily do.
Yeah, that's an ongoing debate in the AI community, and you have on one hand people who will linear extrapolate on a rectilinear grid and say, we've been trying to do that for 50 years and making incremental progress, so it's so far out in the future that don't even think about it. You have other people who plot Moore's law on semi-log, plot and extrapolate linearly to that and say, we have an exponential build up in our capability and we're almost at the tipping point now. So you've got these two very different views of where we are in the process, and I don't know that anyone fully understands it, but it's clear that our current approaches we're not taking sufficient advantage of what we're already learning about the brain and using that bio-inspiration to create better architectures, that are more hierarchical, that are iterative in the way they learn. The learning itself is not a flat training process. It's a very hierarchical process, and there's a lot of stochasticity, as you say, in the way human brains work that is not part of our machines at the moment.
Yeah, I love that idea of bringing some of this messy way that we think and intuit and putting that into a machine, which I think ought not to do that, but what an interesting idea. So let me now swing back over to the left. Sir?
Thank you, John Crockett from San Diego State University. My preference would be to keep the human in the system, so let's let the human do the messy stuff. And if we're basically good for all three components, if what we bring to the table is maybe intuition, creativity, maybe a little imagination, our university systems are not particularly well suited to training those types of things. So as our interests in sort of advancing the technology sort of begin to outstrip our capabilities, are there things that we should be thinking about or different ways to engage DARPA, or from your perspective at DARPA, to modify our training systems so that we're still training people that can take advantage of these new technologies and these new opportunities that we're imagining with intuition and creativity and imagination?
If no one else will take that, I'll throw out my 2 cents. I mean, it's a great question, and it goes to highlight that we're wondering why we can't train our machines to think creatively, but in fact, we don't even know how to train ourselves to really think creatively, because it's such an undefined process, and it seems to come out of the blue, and we're not fully sure how we ourselves somehow connected these totally different pieces and came up with the solution, probably in our sleep. And I agree, it's absolutely not part of the training process in certainly K through 12. It's almost drummed out of you. So I think the universities, it's a better system, but whether we can do better or not, I'm not qualified to answer.
I am.
Okay.
You'll take it.
I am a Luddite. Force them to write critical, thinking-oriented documents and have them do it over and over and over again, and don't offer a course that doesn't force them into that. And you will end up with your desired results, right?
We might lose some of the business majors.
Hey, look, 1940s, 1950s, right? We built a lot of what we're looking at today, and that was built by people a generation before who were getting educated in a one-room schoolhouse and then maybe going to Harvard. Someone went off to the war and then came back and began to make their discoveries, all right? So I think we have gotten a little too, let's figure out this secret. The secret is, if you can articulate yourself in writing, in my opinion, you have to have the creative capability to start to intuit and think beyond. Because writing and being able to extract what you're thinking out of your head and put it down in a cogent way is actually, in my opinion, the best template for what we all do.
Okay, we're getting down to the last 5 or 6 minutes, so if possible, let's try to make our comments and questions concise, if possible, so we can maybe get everybody to have an opportunity. Let's go to the middle.
Hi, my name is John Bachman. I'm a graduate student in systems biology at Harvard Medical School, and I wanted to respond to Jim's example or thought experiment, in a sense, of could the machine learning algorithms of today distill Newton's laws from a data set of 1 million images. And I think what that example sort of points out to me is I think that there's a cultural bottleneck within scientific communities right now, which is between the top-down empiricists that embrace big data and machine learning and the bottom-up mechanists who use modeling and other tools like that. And in many fields, including my own in systems biology, there's a really stark divide between those two camps. The top-down omics community came from genetics and genomics, and the bottom-up came from biophysics and cell biology, for example. And you see this in AI, where you had the old-fashioned logic and planning, and now you have people who are very definitively declare the unreasonable effectiveness of data and aren't interested in those other methods. It seems to me that there's going to be a big payoff in devising new methods and also perhaps new training or new collaborations that can really exploit the fusion of bottom-up and top-down methods. So just wondering if you could comment on that.
Yeah, I completely agree. I think that's probably more in the domain of mathematics, but we're doing a very poor job of constraining our models. We either constrain them, try to constrain them with the data, or we try to constrain them with the physics or the biology that we already know, but we do not combine those two constraints in a useful way that's more than the sum of the parts. And I think I'm starting to see some ideas about ways to do that, but it's probably in the domain of mathematics.
In fact, this is one of the focus areas that I wanted to talk about why mathematical research now should change, because traditionally when mathematical modeling was done, a lot of times was trying to come up with a very sort of a simplified, maybe a description of the complex system, complex phenomena that was happening, and trying to describe it in simpler terms. For example, maybe an equation, for example, whether it's ordinary differential equation, partial differential equation. And the issue is that for the more complex systems you're looking at, this kind of modeling doesn't work, right? And so that's why I'm thinking that, but at the same time, when it works, it's extremely effective, right? Prior to the paper that he's talking about, unreasonable effectiveness of data is also unreasonable effectiveness of mathematics, right? In physical sciences. So, so that's why I was thinking that really they should come together, right? We have now different tools. I do think of basically data and computational way of thinking as different tools, right? And they're available to us. So if we can actually use them and try to use that in the context of more of the analytical way of thinking that mathematical, modeling can provide, that's when, I think that's where they're gonna get together. Basically, they're gonna, the top, bottom up and up. They're going to meet in the middle. But that's tough. It's actually not very easy. We're trying. You see that in physical sciences, right? You're talking about chemistry. We see that in material science. You see that in biology, that these issues are, those are the challenges. You actually change the way, because we have so much data, data has to come into your modeling aspect.
So we're getting really down to the wire now, maybe one, possibly two more questions. So we're now over to the right-hand mic.
Great. I'm Eric Jonas. I'm a postdoc at UC Berkeley. I sit kind of between the applied and theoretical math teams. And I wanted to ask, this is more a general question about DSO and DSO's role in kind of enabling these sorts of mathematical tools and advanced mathematical modeling. On one hand, we have, DSO funds a lot of scientists doing path-breaking science. They fund a lot of mathematicians. But somehow it seems like all the interesting tools for doing things like modeling are actually coming out of I2O, right? You have Xdata funding tools like CVX. You have PAML funding these probabilistic programming languages. And when I go and talk to my friends doing actual kind of, in the trenches science, they're not necessarily clamoring for more advanced mathematical frameworks. They're clamoring for tools that actually enable them to use maybe math from, let's say, 10 years ago or 15 years ago in their data. How does DSO see its role in enabling that kind of science? Or is that something that really belongs more in kind of, the I2O camp?
Who wants to take it?
My take?
Sure, go ahead. Anybody?
So from my perspective, I have to take my shoes off to count to 20. So in my programs, I recognize the need, and I run down the hall and talk to Fariba, and she helps me write the words that are going to help me get that in my program, and then I have her help me evaluate. So that's my take on it. I need it sometimes.
Okay, so you want to say something? That's it. All right, so we are down to the last question. It means, sir, that you have to ask the best question of the entire day.
I appreciate the challenge. I doubt I'll live up to it. Greg Engel, University of Chicago, and I was very curious in the chemistry talk, the focus on structure and the number of configurations, but it seems like if we want to create novel materials and functional materials, we need to understand the dynamics that link structure to function, and that seems somewhat absent as we're trying to increase the field of view of our nanoscopy or 3D print one molecule at a time. We need to understand what these things do, and it seems like this chemical dynamics on the picosecond or femtosecond time scale and how they move is more important in some sense than putting the atoms where you want them. Do we have tools to go after that? How do we approach that problem?
Short answer.
Yeah, I think that's a great question, and I rely on my brilliant colleague Prem Kumar to worry about those aspects because he understands picosecond, femtosecond laser spectroscopy and shape pulses a lot better than I do. So the dynamic side of it, I think, requires that time domain. I can't even write down the time-dependent Schrodinger equation. So I'm more of kind of let's chisel it, let's build it together, and Prem is actually got programs running down those directions. So it's absolutely important. We just got to have the right person, not me.
Okay, so this, just in closing, a few things. One, I want to thank all of you for deciding to come to this breakout session because you had 6 to choose from, so we're very grateful that you joined us. Also grateful that you joined us in such an engaged way. All of your questions were absolutely fascinating. Wish we could have gone on for hours. And there are ways of continuing the discussion. We didn't even get to the question we wanted to ask you, which is, what do you think is the next great disruption and why? But you can go to the survey question that DSO has put there, and you can actually respond to those questions, to that question. And so I just want to give you a hand for coming and being so engaged. And thank you to our speakers.